Let's take a look at a free body diagram. Free body diagram is a tool that allows us to analyze a situation where forces are involved, usually with the goal of trying to determine the net force, although sometimes we're working backward to find individual forces as well. If you look at this picture, the man is pushing against the car. That provides us with one rather obvious force, a force being applied to the right that we would just label FA with an arrow pointing in the direction of the force acting on the car. Another force that's fairly evident is the weight of the car. The car is experiencing a gravitational pull down toward the center of the Earth. We label that FG. Gravity is always down. In the Earth frame of reference, it will sometimes, however, be labeled with a W instead of an FG. We know that the car is not being accelerated down toward the center of the Earth. It's held there in place by the road. And what we describe that force as, that supporting force, is a normal force. It's perpendicular to the surface. And as long as the surface is level and there isn't anything else kind of strange going on with the situation, the normal force is going to be equal to the gravitational force. Either way, as long as we know the car's not accelerating up or down, we know that these two forces have to balance each other out. There's an additional force that is probably here. We're on Earth, and so we are typically going to be experiencing frictional forces. The effort that this man is exerting also suggests that he's working against some friction as well. So that force, we don't know the magnitude of that force. If the car is not accelerating, then we know the frictional force has to equal the applied force, but this is a still shot, so we really don't know what's going on with the motion of that car. Let's take a look at some examples of net force. Our first free body diagram here shows three forces acting on this object. Two of those forces are acting opposite to each other, and they are equal in magnitude, and so they're going to cancel each other out and not contribute to the overall force in any meaningful way. There is one extra force that's unbalanced here, 5 newtons in the downward direction, which means the net force acting on this object is simply the 5 Newton force, and the direction is down. In example 2, we still have the 5 Newton force pushing to the right and 5 Newton force pushing to the left, but now we also have two forces acting vertically, 2 newtons down, 2 newtons up. They cancel each other out as well because they're equal and opposite directions. When we subtract everything out here, we end up with nothing as our net force. So our net force in this example is 0. This object is either at rest or it's traveling at a constant velocity. In example 3, we again have 4 forces. 2 of them are equal and opposite to each other, the left and right forces of 2 newtons each, so those cancel each other out. The vertical forces, however, are opposite but not equal. They're unbalanced. So in order to find the force acting vertically, we have to subtract the two. 5 newtons minus 2 newtons gives us a 3 Newton force in the direction of the larger force, which is down. In the fourth example, we have 3 forces that do not cancel out in either the vertical or the horizontal direction. Solving this problem requires us to use some trigonometry, and we're not really ready to do that yet, so let's ignore that one. Let's try to put it all together and do an example where we're given a description of an object and we're asked to complete a free body diagram. In this description, the first thing that stands out to me when reading it is that there is a constant velocity acting on this object. So that tells me, without going any further, that the net force acting on this object has to be 0. You cannot have a constant velocity associated with a net force that's not 0. Net forces always cause acceleration. So that tells me that when I'm finished with my diagram, I better have all my forces balanced, or I'm not going to produce the correct free body diagram. So as we read, it says a 35 Newton ball is rolling. It tells us a couple of things. When the force, 35 newtons, is used as an adjective to describe the ball, that's usually trying to tell you its weight. So there is a force pulling down on this ball, that is the gravitational force, and it is equal to 35 newtons. Weight and gravitational force are the same thing. It's rolling along the ground, which tells us that there's a force that's pushing it up as well. Sorry, let me get that straightened out for you. A force that's pushing upward, supporting the ball as it rolls. This force is going to be equal to 35 newtons as well because it balances out the downward force, and we would call this a normal force because it is a support force acting perpendicular to the ground. We're also told specifically that there is a frictional force acting to the right and that it has a value of 12 newtons. And we are not told anything about an applied force, but we know that there must be something pushing to the left there, and that force might as well be called an applied force. It really could be anything without any other information, but we know for sure that there's something over there, and it's got to be worth 12 newtons. Here we see an example that describes an upward moving rocket. So this is an object that has a motion that's in the upward direction. That doesn't go directly onto our free body diagram, but it does help us determine some of the directions of our forces. It says the net force acting on this object is 300 newtons up. So I'm going to make a note, net force 300 newtons. That's important to remember. You're asked to figure out the applied force if the air resistance is 200 newtons. So one of the forces that has to go in our diagram is air resistance. Air resistance acts in the opposite direction of motion. So if we've got a rocket that's moving up, the air resistance force is going to be moving down. I'm just going to call it F air, and that's equal to 200 newtons given to us in the problem. And we're asked to figure out what is the applied force up here if the net force is 300. Well, whatever that applied force is going to be giving up 200 newtons of force to air resistance. So if you're going to give up 200 newtons of force and still have 300 newtons of net force left, then you must have started with an applied force that's 300 units bigger than the air resistance force, or 500 newtons in the upward direction.